Welcome back to Western Washington University. I'm Aaron Clausen, and Sean Basler is behind the camera and, quite frankly, behind the project. So if you're tuning in for the first time, this is the continuation of our IEEE-754 content. If you want to see the previous video, there's a link below that you can follow to learn all about IEEE-754 in its normal form. Today we're going to talk about some of the abnormal forms. But before we get there, let's start with an example. So if I take 1/8 and I want to encode this in the 754 format, and just like last time, I'm going to stick with the single precision float, the 32-bit number. The first thing I need to do is convert this into its binary scientific notation. And we learned a trick last time about multiplying by 2 and comparing to 1. But this is going to be a lot easier, because I know this is the same as 1/2 to the third, which I can immediately put into scientific notation as 1 times 2 to the minus third. So now it's just simply a matter of encoding. And if you remember, the encoding is a sign bit, an exponent bit, or bits, so I've got my sign bit, my 8 exponent bits, and if you remember, they're biased by 127. And then my 23 fraction bits. So the sign is easy. 1/8 is positive. It's not a negative number. The exponent bits, I need to encode my -3 by subtracting 3 off of 127. And we can actually do the math, which isn't difficult, or we can remember we just flip the bits for our negative exponent. So 0, 1, 1, 1, 1, 1, 0, 0. And then I have to encode this 1. And remember, there's an implied 1 that sort of hides right in here. It's actually not part of the encoded information. We just assume that that 1 is there. And then 23 zeros. So this is actually the encoding of 1/8. Now this is where we need some not so normal forms. I would like to be able to encode some really small numbers, and the number I'm thinking of is 0. Well, if this implied 1 is always there, I can't ever represent 0 exactly. The best I could get is 1 times 2 to some, I guess, minus 127 because of the bias. That would be as small as I could represent, unless I have some exceptions. And here's the exception I want to talk about. It's technically referred to as denormalized form. And the way we know it's denormalized is with an all 0 exponent. So there's my sign bit. Here's my exponent. And the fact that it's all zeros tells me this is a denormalized number. And then I have my 23 fraction bits. In denormalized form, that implied 1 that lived right here becomes an implied 0. The other thing we have to remember is this looks like times 2 to the minus 127. It's actually going to be times 2 to the minus 126. Slightly larger than you would expect. What this accounts for is that this implied 1 became an implied 0. And now it's just whatever the numbers are. So 1, 0, 0, 0, 0 would actually be 0.1, which equals 1 times 2 to the minus 127. If we were to multiply this number by 2 for some reason, I would want this to become minus 126. I would actually shift this up a bit, which would shift it into the implied location. And I'm no longer denormalized. And that's why that exponent in denormalized form is a little off from what you'd expect. So this would actually be 1 times 2 to the minus 126. Well, in denormalized form, I can now represent the value 0 because of that implied 0. So this 0 sign, 0 exponent, because of the 0 exponent, it's denormalized, the implied 0, and all zeros in the fraction bit means 0. 0.0, however far I want to go, times 2 to the minus 126. In this case, I really don't care what the exponent is on the 2, because I'm multiplying it by 0. This actually equals 0, which makes it easy to identify a 0 in floating point numbers. It's the same bit pattern as 0 as an integer. And yes, there is some weirdness. We can actually encode negative 0. Let's just agree that negative 0 and 0 are the same number. But it lets me encode something very small that I couldn't before. If I have a 0 exponent and all zeros except 1 out in the 23rd bit, I can encode a very small number, which is going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 times 2 to the minus 126. Normalized form, minus 126. This equals 1 times 2 to the... I can shift that binary point 23 positions. Minus 126 minus 23 gives me minus 149. In the single precision float, this is the smallest positive number that I can represent. If I go just a little bit smaller, it becomes 0. So let's go to the other end of the spectrum. So we know that if the exponent bits are all 0, we go into this denormalized form and the implied 1 goes away. It becomes an implied 0. Well, at the other extreme, we go into another special case. The other extreme is infinity. And so when the exponent is all 1, you can think of the implied 1 here, or the implied 0 in denormalized form, becoming an implied infinity. So if I have a 0 sign bit, an all 1 exponent, so 255, we minus off the 200 or 127, this should be 127 as a positive exponent. We reserve it as a special case. So all 1 exponent, our implied 1 becomes an implied infinity. And with all zeros as the fraction bit, it's infinity. But here's where some weird things happen. What happens if I increase my fraction just a little bit? I put a 1 in there. So now I'm talking about something that is slightly larger than infinity. We give this a name in computer science. Suddenly this stops being infinity and becomes nan, which stands for not a number. The easy way to remember this is there are no numbers larger than infinity. So if there's something in the fraction, you're trying to express something larger than infinity, and that's simply not a number. Nans and infinity are kind of nice to work with. In the infinity case, it's referred to as saturation math. If the numbers that you're trying to represent in your float get so large that it would otherwise overflow, and so for integers, if you overflow an integer, it becomes really small. In the floating points, it becomes infinity and just sits there. If I add to infinity, it's infinity. If I divide infinity by 2, it's still infinity. And it just lets you know that if infinity is your result, it ran out of bits. Use a larger data structure, or larger type. Nan is actually used to sort of taint your calculation. This is a nice way to start a calculation if you didn't get any input. Because nan will never result in anything other than a nan. I start with a nan, I multiply by 5, I multiply by 0, I divide by 10. Once it's a nan, it's always a nan. the calculation is total garbage. So if you have some value that you need an initialization value that you don't want to get into a calculation, nan is a good choice. If you get nan as your output, it means you didn't give it a valid input. And if you get infinity as output, it means you ran out of bits. So let's summarize these last two videos. The last video we talked about normal form, which basically gives us, if we talk about a sign bit, our 8 exponent bits and our 23 fraction bits, we can encode a number as -1 to our sign bit. That gives us a -1 if the sign is 1 and a 0, or a 1 if the sign is 0, times 1 point fraction, whatever those fraction bits are, times 2 to our exponent minus 127. Remember, we have that 127 bias that we need to subtract off whatever these bits mean. So that's our normal form. This assumes that our exponent is not all zeros and not all ones. So this is our normal form. Our denormalized form would be -1 sign, 0 point fraction, and this is even easier. I don't have to do any math with the exponent. Denormalized means our exponent is all zeros, and I know that just means times 2 to the minus 127. And then our last case is our infinities and our nans. So if the exponent is all ones, I either have infinity if our fraction equals 0, or I have something that is not a number if the fraction is something other than all zeros. So this is where we're going to live most of the time. This gives us some value, possibly positive or negative, of reasonable size. Denormalized form gives us this little extra range as we get close to 0, and a sensible way to encode 0, all zeros. It gives us a little oddity with -0. Not really sure what that means. We'll just call it 0. And then we have a way to encode positive and negative infinity. If our calculation gets too big, we can't encode it. We get some results that mean something. And a way to encode something that just simply isn't a number, and we'll just taint the rest of our calculation, letting us know that we forgot to give it an input. So we have normal form, denormalized form, infinity, and nan. And that's what we're able to express with the IEEE 754 floating point form.